of me. So two important sort of announcements. Number one is my math lab. For those interested in the extra credit, this will be running, or will be up on Canvas tonight. So I set the wheels in motion. Once Pearson finalizes the course, they'll send me an email that it's ready, and then I'll send you the instructions for how to log on if you want to do it. If you have any questions about the My Math Lab, just let me know. It's not required. It's just extra credit for those of you who bought the passcode or the actual book. Fair? It's not 100%. Or excuse me, it cannot negatively affect you. The only thing it do is the extra credit. Cool? So I wanted to say that, and then what else did I want to say? Oh yeah, don't forget that everything should be, I don't know if those of you who use your phones or tablets, but when I log into, let me show you guys this, because I want to make sure everybody knows where everything's located on so when you log into Canvas, this is what you should see. And by the way, those of you at home, you're not seeing this right now. You're still seeing the whiteboard. But if you log into Canvas, you should be seeing everything you need on the front page. Homework assignments, the lecture slides. The YouTube lectures are embedded right there if you want to watch them. You don't have to, but they're there if you want. Right? So everything you need is right here. If there's something you can't find that you do want, just email me. I think one of you emailed me Friday or Thursday. Did I get it up quick enough? I don't even remember. If I didn't, I'm sorry. But it's a process to get these things up, believe it or not. So I try to get them up as soon as I can. So if you need anything, you just don't hesitate to email me. All right. All right, cool. So does anybody have any questions about anything related to the course? Not any math, but logistics. We good? Everybody found the syllabus, read it. Oh, don't forget, you're going to have your those little weekly quizzes. I got to give you one for week 1. They're not going to be difficult. The longest they'll be is I might ask you to watch a video and answer questions about it, something like that, like a 10-minute video or something like that. Or it just could be couple simple questions. It's a way to build points for you guys. All right, so good. Let's get back to class. So we're going to do a famous example right now to get us in the groove. So first one we're going to do is a pyramid. And then the second one we're going to do is a cone. And then we're going to generalize. So I always find that this is the sort of the way to do it. We're going to take two sort of famous shapes. We're going to analyze and figure out how we might define their volume or compute it if we believe that there's this thing we can do. And then we'll go from there. So let's draw a pyramid. And we're going to try to be as sort of thorough with this as we can. So in order to do this, we kind of have to, let's see if we can sort of make this, we got to try to make the base a certain way. I'm going to try to make this as useful as I can. What if I can tilt this thing? No, I guess not. All right, so you have to imagine this is some three-dimensional object, okay? Now, for simplicity, we don't have to do this, but we're going to assume that it has a square base. Does that make sense? So let's assume that one's in there. So let's assume that it has some square base, x by x, and then it has a height of h. So think of this problem in two different ways. We have a notion in our head, an intuitive notion of what volume means, right? I mean, we have a, how much, you know, you want to think about volume, you might say, how much liquid can I put in this cup or something like that, right? So we have an idea of that. And what we had to do, if you remember last class, we defined volume for two types of objects. We said, imagine a box or like a brick or something like that. That we said its size, its volume is length, width, height. That's what you learn as a kid when you talk about it like a rectangular thing. And so we're going to try to use that to our advantage. So here's the idea. The idea is to, let's take a horizontal slice. So what might that look like? Well, that might look like this. Let's get a good color. So that might look like this. Take this. That was bad. So this slice can be pulled out. So let's pull it out. Imagine it looks like this. That's a bad way of drawing. Let me sort of. Got to draw in perspective. So what does this look like in perspective? It looks like this. So it has a little bit of a thickness, and it has a width. So this is a, you know, it's not really a square or a box, because if you think about it, its sides are slightly angled because it's on a pyramid. So you would imagine that this is sort of like an angle. These are sort of angled. And by the way, it has this depth, so we can illustrate that with sort of like these dotted lines. So the way you want to think about it is the volume of this slice is approximately the volume of a rectangular prism. Or the fancy word is like parallel piping. Now, I didn't say anything about this slice. I happened to draw it about halfway up, but I didn't say where it was located. One of the things you'll notice is if a slice is towards the bottom, it's going to have wider sides than if it's towards the top. Does that make sense? Like a slice, if I take something up top, at least intuitively, a slice up here, the slice up here is going to be smaller than a slice where this blue guy is, and that's in turn going to be smaller than a slice down below. So in general way of saying that is the size of each slice depends on how high it is. Does that make sense? So if I can draw, what I can do here is I can say, okay, good. Let's put this, and let's say that this is approximately the same thing as, let's say this one has straight sides. When I say sides, what I mean is these corners. Imagine a pyramid has this slope to it, whereas the box won't. So this thing is going to be like this. And the reason that that's important is we know the volume of the slice on the right because it's a prism. It has perpendicular sides. And imagine if this slice is very thin, it's going to be even more approximated by this thing, right? Does anybody have a question about that? So a good way to think about what I'm saying is imagine you had lots of paper and you started with a square piece of paper. And then you took another piece and you just cut it so that it's a little smaller around the edges and place it on top and did that. That's one way to build a pyramid. You'd imagine that pyramid has steps almost, right? But we want to think of a pyramid as being smooth. And so here, the key observation is that this is perpendicular. Everything over here, these are all right angles. Over here, they're not. We understand what I'm saying here? If you don't, please ask. Okay, so now, how many slices do we want to take? Do we want to do 3? Well, that would be a pretty bad approximation. Do we want to do 100? Well, that might be good, but that would be time consuming. Right? But in theory, we could take 1 slice, 2 slices, 3. We could take 1,000,000 slices if we wanted. Do we understand that? Just like if you've ever seen a loaf of bread before it's sliced, you can cut a loaf of bread into any number of slices you want. You ever notice how when you buy fresh bread, if you don't eat it like in a couple of days, it goes bad? Makes you wonder why you eat that shit like the Giant Eagle stuff when you have it in your cupboard for like 3 weeks and it doesn't go bad, right? You ever want that makes you think what they're putting in your food. Seriously, go to the deli and buy fresh bread and see how long it lasts in your cupboard, and then buy the 99-cent Giant Eagle bread and see how long that'll last. All right. Okay, so very good. That's we have all these right angles here. Okay, so here's what we're going to say. Let's take n slices. So let V sub k be the volume of the kth slice. Where k can be 1, 2, 3, it can be any number, right? Any positive integer. So I'm going to go through this example, as you can see, very slowly. And I hope you'll really take the time to study it, because when we're going to do the other ones, we can't go this slow. We'll never get anywhere. We'll be stuck in chapter 6 or 7 forever. We can't do that. All the fun's in chapters 8, 9, and 10. There's a lot of good analogies I could have used right there. but I like my job. Although I already said ship once today, and it's on record. You can have me fired. Wait till you see the replacement, though. All right, so, okay, what is the volume of this slice? How would we even begin to look at the volume? Clearly, if it's at the bottom, it's going to have a different volume than if it's at the top. So what we need to figure out is we need to figure out what geometric sort of ideas are at our disposal. What information do we have about the volume? All right, so what we need to do now is we need to approximate V sub k using the rectangular prism. Yeah, spell prism with a Z. It's like an S. Yeah, that's like the O'Grady version. I don't think that's how you spell prism. We'll let it spell it like this. Anyhow. All right, so a good way to do this is to look at, oftentimes when we're very confused about something, or not necessarily confused, but when we're not sure how to handle it, sometimes it's useful to simplify things. So if I take a pyramid and I put it on the floor and I stand way above it and I look down on it, it looks like a square. Just like if you ever saw an orange traffic cone and you set it on the ground, and, well, that's a bad example because they usually have a square base, but imagine, take an ice cream cone and put it upside down, like one of those waffle ones, you know what I'm talking about, the cone, it's going to look like a circle, right? From that perspective, it's going to look like a circle. Now, a pyramid from one perspective, from up top, looks like a square. However, if I look at a pyramid from far away on a side, it's going to look like a triangle. Are we clear with that? So, on another perspective, so if I look at this, if I take my pink pyramid and I spin it so that one side is directly facing at me and I step back, it's going to look like a triangle. Another way to think about that is if you shine the light on it from that direction, the shadow it makes would be a triangle. We call that a projection. So if I take my pyramid and I project it from 3 dimensions into 2, if I put a shadow on it, looking down, the shadow is a square. From the side, the shadow is a triangle. And if we project down, if we look at that shadow of the triangle, it's going to give us information on how we can determine the volume of that slice at any given point. Is that clear? So let's draw a picture. And so what I'm going to do is I'm going to get my triangle. So we know that the base, oh no, I wanted pink. We know if we label it that this is the base, let's fix that. It's like a trunk base. Level off, homie. And then what I want to do is I want to label a couple things. First off, I'm going to draw a perpendicular. Whoa, boy, that got out of hand. So first thing you need to note is that this is a right angle. And knowing what we know, let's draw our slice, our blue slice, to be consistent, was up here. So we know that downstairs the total distance is x. So let's call this line 1/2 x, and we'll call this guy 1/2 x. Does that make sense? Because it's half of it. And then we also have some information. Maybe I should have, okay, that's okay. So we also know that the height of this thing, the total distance is h, right? And so that means we can measure then the height of the blue guy. What is the height of the blue? So in particular,
yeah, but they,
what do we have? If the total height is h, what can we say about the distance from the blue line down to the bottom? Well, one of the things you learned in high school geometry was this thing called similar triangles. And they beat the hell out of it, and then you guys had to write these problems like side, angle, side, and all blah, blah. Now you think, when am I ever going to use that? Well, today you get to use it. So using similar triangles, so it might be useful to give these guys names. So let's, creatively enough, let's call this point A. We can call this point B, C, and then we can call this point D, A, B, C, D, E, F, G, H, I, J, K, L, M, N, P. Now we want to give this a name here. We don't know what this guy is, so we'll call, I don't know, what's a good thing to call this creature? So here's what I want you to know. First off, triangle A, B, C is similar to triangle A, D, E. And so that means that they have to have these ratios of their sides have to be in proportion. So a good way to do this is to think about this thing sitting in a coordinate system. That's one way to do it. We want to give this creature a name. So let's call, for the sake of we don't know what else to do, let's call this distance lowercase a. We want to think about this distance from here to here, and we want to think about this distance. Okay, that's misleading. Let me, and then we want to, what is this distance from the blue line down to the ground? Does anybody have a question? Okay, so we want to fill in these blanks. Here's what we know. We got to give these guys names. So just for the sake of it, I call this lowercase a. I'll call this lowercase b. And I'll call this lowercase c for now. And we're going to rename these when it's useful, but for now we're just going to, we know their numbers, we just don't know what they are. So here's what we know. We know in similar triangles, and again, if you have to Google similar triangles and remember some of their properties, that's fine. But what can we say? Well, we could say the following. We could say, so 1/2 x has to be, when it's divided by a little a, this has to be equal to total distance divided by what? B. So think about this carefully. The big triangle is ADE. Inside of it is ABC. So what we're telling you is we're telling you that the base of the big one divided by the base of the small one has to be equal to the leg of the big one divided by the leg of the small one. That's one way to interpret it. We okay with that? Now, why is this important? Well, remember, what we're really interested in is we need to know A, little a. Little a tells us half of the length of our slice. So what we really want is we want to know what A is. So if we do a little algebra, what is A equal to? Well, A is equal to 1/2 B times X all over H. Or if you want, you could write it a little cleaner. A equals BX over 2H. Now, does anybody want to say anything? Have a question? Okay. So what good is this? Well, I don't know yet. But the good news is, the very useful news is we now know, at least for our slice on the previous page, this rectangular prism on the right, we now know the area of it, at least its length and its width. Now, we haven't said how thick we want our slice to be yet, have we? No, and what we have to understand is that thickness of our slice is going to depend on how many slices we choose. The more slices we make, the thinner they're going to be, right? Because the pyramid's only so big. If I want to break it into 3 slices, then I'm going to have thick slices. If I want 100 slices, they're going to be very thin. So the number for the thickness of our slice is going to depend on how many we choose. We can now put this together, though. So now we're going to use, as I mentioned earlier, we have sort of like a puzzle. You can think of what we're doing as we're building a puzzle. If you've ever built puzzles before, what do? I mean, one strategy is to take the pieces out and then organize. I'm going to put all the edges here. I'm going to put all the colors that have red here or blue, right? And there's a strategy to that. And then at some point, you have to put the pieces to the puzzle together. That's what we're trying to do right now. Right now, we're just trying to get information. I now know how I can compute the area, the volume of my slice. I now know what that is. You might not see it, but I see it. And that means I can put the puzzle together now. So what I'm going to do is the following. So let's slice our pyramid into n slices. V1, V2, V sub 3, all the way up to V sub n. And what I'm going to do is I'm going to draw that picture again. I'm going to do it a little quicker this time because it's important that we see it. And I'm going to give some variables into the mix. Actually, what we can do, which would be a little easier, let's just look at half the picture because really only half of it is important. So I have my slice here. Very good. I know that this down here is 1/2 x. I know this number is a. I know the total height is h. So I need to introduce, so, you know, we already know my ultimate goal is to integrate, right? I hope you guys realize that. And because we're doing the same strategy that we did for area and before, is that as you slice whatever you're interested up into small pieces, examine those pieces using a known fact, that gives you an approximation. And as you use more and more slices, that approximation ends up having a limit as the number of slices increase. And that limit is given by the integral. Okay, so what do we call the other sides? Well, we had b. So if this is b from here to here, then what is the distance from here to here? Well, this would be h minus b. Does that make sense? So now we have to give these guys all, for simplicity, we'll say that they all have the same width. So, or height, I should say. Now I'm going to use the letter y because I've already used x. So y is going to be sort of my variable. So let this point right here, let's think of this as a point on a number line. So it's useful to set y equal to h minus b. And so then if we do that, so that means that this is height y. That means this is y. So at height y, v sub k is approximately what? Well, it's approximately going to be 2 times a times the height, dy. So again, it might help if I sort of draw this. You think of this slice as having a height to it. So we can sort of illustrate that like this. That's delta y. Now, what is this number 2a? Well, we know 2a, that depends. A depends on how high it is. We saw that on the previous page. In fact, we know a is bx over 2h. So this becomes 2 times bx over 2h delta y. Now we have a lot of letters floating around, and that's not good. But what we need to do is we realize some are variables and some aren't. X is not a variable. X is fixed. X was the width of our pyramid originally. X is fixed, so we don't have to worry about that. It's a number. However, B and H depend on each other. H is also fixed, but what is not fixed is B. So the first thing you note is the 2's cancel. And then what do we want to do? Well, we need to write B. So this 2 cancels with this 2. And instead of using B, we want to use, we could use B, but it's going to turn out to be a little more useful if we instead, we write this as 1 over H And then instead of b, what is b equal to? Well, b can be rewritten in terms of things that are of use. In particular, I can write b as h minus y delta y. So I'm just rewriting this. Now you might say, why are you rewriting it? Because what I'm trying to do is get two things accomplished. Not only do I want to have an expression for the volume of each slice, but I want to build it in a way that I obtain a Riemann sum in the end. That's the reason I sliced it this way. I want to build a Riemann sum. Now, this is a Riemann sum is going to be hidden here. You might not see it because you're so used to thinking as x as the variable. But now the variable here is y. This thing, you can imagine this triangle that I have drawn right here, this point right here, this black dot, I imagine as y goes from 0 to h, that dot moves up and down. And then that means this this blue slice, the higher up I go, that slice is not as wide. The lower I go, it's wider. Now, there's one thing we should do here to make this much more specific. Yeah. Say that again. What about the x? Yeah, I forgot it, right? We can fix that.
Get washed.
So I've written it this way for one, because x and h aren't variables, they're fixed, correct? The only thing that's a variable is y. Now, if I'm being even more careful, what I should note is y can't take on any value. It has to be one of n values. Actually, it can be one of n plus 1 values. It could be height of 0. It can be delta y. It can be 2 delta y, 3 delta, right? Do we understand that? So really what I should do is I should call this y sub k, because I'm chopping the h up into n pieces. So the more you think about how an integral is defined with a Riemann sum, the more sort of this makes sense. And I'm not pretending that this is easy to learn either. It's a difficult idea, but it's important. Again, we got software to compute integrals for you. What you need to understand is why they're important. Why is an integral important? Not that you can compute them. That's what the calculator's for. That's what Wolfram's for. You need to understand what an integral actually means, not that you can plug it into something, right? So that's what I would sort of encourage you to think about here, building this up. Okay, so fair. So what we do then, is we add them up. So if V equals the actual volume of the pyramid, V is approximately the sum as, say, K goes from 1 to N of the V sub Ks. Now we know what these are. The V sub Ks can be approximated by that formula from the previous page. And what was the formula from the previous page? We had x over h times the quantity h minus y sub k delta y. So since this is a Riemann sum, we can send n to infinity, and what we get is a beautiful formula. The volume is actually equal to the integral from 0 to h, because that's how y ranges, of x over h times h minus y dy. Now, one of the things that's overwhelming when you're in calculus 2 is that you see all these letters like this. If I gave you an integral from like 1 to 3 of, a polynomial, you guys are great. When you see this, you're like very overwhelmed, but let's compute it and let's make sure this agrees with what you may have learned as a kid. First, we better make sure that we got the formula down correct. It looks like we did. And by the way, one of the nice things is this is the only problem that's going to take us long. Because once we understand the pattern that made this work, we can apply it. And that's the beauty of math and finding patterns. We find patterns that turn really difficult things into simple things. This only took us a long time because we wrote it out so that we see the hidden pattern. Once you see the hidden pattern, all the long steps in the middle often go away. So we can compute. What is the volume? Well, it goes from 0 to h. I'm going to pull the x over h out because it's constant. So this is y minus y, provided we didn't make any errors, dy. Now, no one has yelled yet if we've made any errors, and it's starting to concern me. So let me go back a page and ask you, have we made any errors? Those of you who've had me before, well, even this summer, though, it's not the same because we weren't in person. I often do this, and one thing that gets annoying to me is when we don't recognize it. There is something missing, and I've alluded to it 3 times now, so let me allude to it one more time so that we can fix it. What is the area of a square? What? Yeah, well, yeah, it's width squared, right? So if I have a slice, like I've drawn here, what is the area or the volume of this? It's this, right? Times this, times its height. So what I did is an error, and you can see it if I point it out now. We found the length here, so we know that 2 of these gives us the side. So that's fine, but what do I have? I have 2a. But that just gives me the length. So what should it be? 2a what? Squared. Heavens to Betsy's. This, my friends, should be squared. Very good. Which means there is a 2 here. I tried to put the damn thing in red too, and no one caught it. So canceling these 2's, we have to be a little more careful. So let's be very careful before we do that. So this is 4a squared. So what is a? Well, let's be very careful. A, we got from the previous page, A is bx over 2h. So that's bx over 2h squared, correct? Okay, that's good. So then, of course, the 4's will eventually cancel. So then you're left with not x over h, but x squared over h squared. And then what is b? B, we know, is h minus y sub k quantity squared. So we forgot our square. Ah, boy, you guys would be terrible NASA engineers. You'd be missing all the planets. Fire, 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 fire. No, look, it's important. There's a reason I do this. It's important that you ask yourself at each step, what are you doing and is it correct? Does it make sense? Now, what would happen, hopefully, if you go through that process and don't get it, is at the end, you get an answer and then you check it and you say, that doesn't make sense. Then you know there's an error somewhere. Okay, so anyhow, we can put our squares in here. And then we put our squares down here. So we're not really, you know, lucky I do it so that we don't mess up too much. Now, there's a couple ways you can evaluate this integral. You could do a substitution, or you could just multiply it out. I'm just going to multiply it out. So you get h squared minus 2hy plus y squared dy. And we're going to integrate now. This becomes h squared y minus hy squared plus 1/3 y cubed. Evaluated from 0 to h. Now, in the middle term, you'll say, what happened to the 2? Well, I divided 2 by 2 is 1, so I didn't write it. Now, when you plug in h, look what happens. This is pretty badass. Every term just becomes what? H cubed. H squared times h is h cubed. H times h squared is h cubed, right? So these guys actually do what? Believe it or not, they cancel out when you plug it in. So let's be very careful here. You get x squared over h squared, and then you're left with h cubed minus h cubed plus 1/3 h cubed. Now, when you plug in 0, everything goes away, so you can just plug this in, minus 0 plus 0 if you want. And so at the end of the day, what happens? You get a 1/3 x squared times h. Woo! That is the volume of a pyramid. The volume of a pyramid, no, we got, well, they're not probably right pyramids in Egypt. We got to go check them out. I want to go see the pyramids. You ever seen the pyramids? Anybody ever seen pyramids in person? I heard they're not that cool once you're there, but I got to go see the pyramids. Go see the Nile River. Take a swim. So the volume of a pyramid is 1/3 the area of its base times its height. It's pretty cool. Let's double check that with the internet. Make sure that we didn't lie. Oh, there's me trying to figure out when I'm going to go golfing. Okay, when do I go golfing? So let's go volume of pyramid, and Wikipedia will, or excuse me, there it is. Look, 1/3 length, width, height. Well, our length and width were the same, so that's why we got x squared h. We got the same thing. What a time to be alive. That was fun. You guys have fun? That was a long process. But there's a hidden secret. The pattern is hidden in there. there was nothing special about a pyramid that we did there. What made the pyramid a good thing to do was that it was easy to use elementary geometry to determine the area of a slice. Does that make sense? But if we could have drawn any other shape, if we know the size of its slice, the area, or what we call more traditionally the cross-sectional area of a slice, if we have a formula for it, we can just do this. So that's the key idea hidden in here. So let's make note of that. Is anybody waiting? I feel bad. All right. So it checked out. The internet tells us we're correct. That's always good. So here's an observation that's key, like your boy, what's it? Khalid will say, DJ, key. It's key. Key. This strategy should work for any solid, provided we have a formula for its cross-sectional area. So if I just draw some sort of shape, we use purple. If I have some sort of, I don't know, let's draw that kind of crazy looking vase thing we had. So if this is sort of like our solid, let's try to give it some depth. So let me draw in another color. If I have a formula for, and let's imagine it's on some axes. So let's draw this one in pink. So let's imagine that I have a coordinate system somewhere. We'll just call it the x-axis. If at some point x, if I know the area of this slice or the area of this cross section, so let A of x equal the area of the cross section slice at x, then the volume would just be, let's call this, let's imagine it's the lowest point is A and then this is B. The volume would just be the integral from A to B of the area, whatever that expression is, dx. That's all we did. I mean, this is going to look scary. You ain't going to just say, oh yeah, it makes sense right now. But after maybe 2 hours of hard thinking from you guys, it'll all come together. Maybe you have a couple coffees or a frappuccino, or what was your drink of choice the weekend? You don't have to tell me. Oh my God. Truly, those are so gross. What's the other thing all the people drink? Ain't no laws when you're drinking the claws. I see you everywhere. I couldn't believe it. They're all gross to me. You ain't even legal. No talking. No, I'm just kidding. You're not legal, are you? No. Oh my God, we have to report you to Sister Candace. It's a dry campus, right? Unless there's events, then they have wine. I didn't say you were. I won't even snitch anyhow. Snitches get stitches. It's funny how some things are considered bad and others aren't. This is probably more addictive and bad for you than alcohol, right? Like, this is terrible. It's like chocolate is like the most addicting thing. You ever just eat chocolate? It's like straight crack to your brain. It's like dopamine rush, right? I mean, you're probably high as a kite after drinking that damn thing. You probably are. But they're like, that's good. Alcohol bad. Think about it. It's so arbitrary and stupid. Anyhow. Does anybody have any questions about this? All right, cool. So here's what we're going to do. Let's now think about this. There's a consequence here. This strategy would work. The only downside is there's two ways to think about this. In practical applications in the real world, you can just slice it up. You don't even need a formula. You can just slice it up and approximate each piece. But like imagine now with modern computing, you can slice something up into 1,000 pieces without much work at all, right? So the computer will add that up real quick. But in the event that there is a pattern and we can get a formula, then we can always be as exact as we want, or exact as we want. We can be exact. So there's something to take from this, and we're going to think about that now. So the bad news is we can't always easily determine that area function, if at all. So that's kind of unfortunate, but there is good news. There are many solids where we can. We just have to think about how one might generate a solid. I mean, think about most solids you encounter. Think about how someone might make it and the different ways that it could be made. So a good mental image, I think, is that when I was a kid in high school, we used to have to take like wood shop and metal shop. I don't know if they still do that for you guys. Did any? Oh, you probably did. I don't know what they taught you back where you came from. Where you came from. What was high school like for you? I don't even know, right? But I know at least here we used to take shop classes, and then if you weren't college material, they say you go do this or that. They called it the vocational. But anyhow, I took a lot of wood shop in middle school and high school. They had this thing called a lathe. Is anybody familiar with a lathe? It's like, think about how you might make a baseball bat. You like baseball, you take a big hunk of wood, you stick it on this metal machine, and then it spins around real fast, and you take something sharp and you sort of cut the baseball bat out of the wood. We can Google this if you'd like. Let me share this with you. Here's a good video. Look at this. What a time to be alive.
A piece of wood, usually ash, is known as the billet. Punch to make an alignment.
Let me show you get to what's important. You start spinning this block of wood, and then they carve it out. With some sort of cutting tools. And then at the end of the day,
take the bat off the lathe and cut off the waste material at each end.
There you go. You've made a bat now. That ain't the lathe. So
tune the shape.
This is the lathe part. So the point is many solids.
While the bat is rotating on the lathe, use a portable finish sander to.
Good. So the point I'm trying to make is that many objects that you encounter that are solids can actually be thought of as being generated by spinning something. You could imagine the reverse process of that you take something and you spin it, and they used to have these in people in their front yards all the time. They don't really see them anymore. They have these little wind ornaments where it was like a piece of plastic, and when the wind blew, it would rotate around a metal thing, and it would almost look like a ball was being made in your mind. So a better way to do it is just to do it, show you a video. So what we want to say is that it turns out that many sort of solids we encounter in the real world can be thought of as being generated by rotating something, revolving something. So here's a good video that helps explain this. Now, what we're saying here is if I take a curve and then I take a straight line, what I can do is I can get a region in the plane, a two-dimensional region. So that's what they're going to draw for you right now. And then sort of think of the idea of a lathe. You take that red region and now you're going to rotate it. And what happens is, you know, you have to have a good imagination. It generates a solid. Notice this solid has a hole in it because of the way we constructed it. And so now they're going to show you what the kind of the ideas we did with the pyramid, where you take this thing that's not actually a disc, but you approximate it with a disc that happens to have a hole in it. Let's see if this video is any good. Anyway, let's see. Maybe this one's better. That one's not loading. Oh, we're done. Oh, here we go. Not the greatest video. That's actually not bad. There's a better visual. So I'd call that like a bullet. Right? It looks like a bullet. And then, as I was alluding to before, you think of a slice and you try to approximate it with something. There's another song. So you got to have an imagination, but I think you guys can all do it. I hope so, at least. Okay. So here's a huge class of solids. These are called the solids of revolution. So you take a region in the plane. And you revolve it around any line. And so what this does is this generates a solid. Now, we don't want to just take any region and any line. We want to pick them so that things are easy, so that we can have formulas. That's the idea. So if we choose a region whose boundary.
I want you to imagine that you have the graph of y equals x squared on a piece of paper in front of you. So consider the entire graph. You only have the segment where x is between 0
Oh my God. Talk to me, brother. I was like, who is talking? Who is talking? All right, so we want to choose a region whose boundary is a continuous curve. And if we rotate about the x-axis, the formula is very simple. Now, it's simple in context. You're going to say it's scary, but it's not. So it's simple in the sense if it would compare to what we would have, all the crap we had to go through with the pyramid. We don't want to have to do that stuff all the time, so we want to recognize patterns. Okay, so here's what we're going to do. Let's draw a picture and think about it. So let's start with our axes. So I'm going to draw them like this. So let's take a region that has a continuous boundary. Let's say, for example, we take this guy. And let's say we're interested between A and B. So we're just interested in this region. So this curve has some rule that allows us to graph it. It's generically, we'll just call it y equals f of x. And the important observation to make is if I pick any point on here, let's just say generically it's x, then this point right here is x comma f of x. Now, if we rotate it about the x-axis, what we end up generating is we generate, I'd call this like a vase, like a vase or a vase. What's it going to look like? Well, imagine that point x comma f of x rotates. So it's going to move in a circle around the x-axis. And so what you're going to end up getting is you're going to get a solid that looks like this. That's not very good. Let's try that again. And the beauty of this is, if we imagine the x-axis going straight through it, the slice at x so if this is our point x, this has area, maybe I'll write that out. What is its area? Well, the slice of that, the cross-sectional area, it's a circle. What's its radius? So its area is pi times the radius squared. But what's its radius? Its radius is the distance from the x-axis to this point on the curve, which is f of x. And so the beauty of this is the volume becomes the integral from a to b of pi times the function squared dx. The name, if you want looks resources up online, this is often called the disk method. And the reason it's called the disk method is because these slices are disks. Right? They're circular disks. Does that make sense? All right, so it's probably a good place to start. We'll give you problems to practice this. You would imagine that the next step would be to take a region whose curve is, the top is a curve and the bottom is a curve. Then when you rotate it, you're going to get a solid that has a hole, sort of like a hole in it. All right, any questions, comments? All right, guys, thank you very much. I will talk to you Thursday. Be safe. Thanks a lot. Take care.